Properties of ionic compounds. Starting with the first property, that is the constituent particles. So, as the name itself suggests, ionic compounds are composed of ions which are opposite in their charges, that is positive ions and negative ions. Positive ions are called cations and negative ions are called anions. We can take a simple example for this. For example, sodium chloride, whose formula is NaCl. Although we write it as NaCl, but it consists of sodium ion Na+ and chloride ion Cl-. Similarly, we can take another example, maybe magnesium fluoride, MgF2, which consists of magnesium ions Mg2+ and fluoride ions F-. Moving on to the second property of ionic compounds, that is their physical nature. Ionic compounds are relatively hard solids. They are solid, and that too hard solids. This is because there is a strong electrostatic force of attraction between the ions of ionic compounds. So if we are saying sodium chloride, which is made up of Na+ and Cl-, obviously when the charges are opposite in nature, they are going to attract each other, and that is why the solid form will be hard in nature. Next property, crystal structure. Now solids are of two types. They can be crystalline or they can be amorphous. Here we are referring to crystalline solids. When we talk about ionic compounds, they are solid in nature and the solids are crystalline in nature. Crystalline means they have a definite pattern of arrangement of their constituent particles. Means the constituent particles which are ions here, they have a definite pattern of arrangement. So which results into definite geometry, and that is why the structure of ionic compounds is crystalline and not amorphous. Like again, we can continue with the example of NaCl. In NaCl, one Na+ is surrounded by 6 Cl-, and similarly one Cl- is surrounded by 6 Na+. So the ions are arranged in a uniform, in a definite manner, which results into a regular three-dimensional arrangement which is called crystal lattice, and so the solids are said to be crystalline in nature. Moving on to the next property, that is solubility. Now there is a saying in chemistry, like dissolves like. The aphorism is like dissolves like, which means compounds of similar nature or materials of similar nature are soluble into each other. So if we are referring to ionic compounds which have a charge separation in the form of positive and negative ions, they are soluble in polar solvents like water, which is the most common solvent called universal solvent. In water there is charge separation, and the similar charge separation is there in ionic compounds. That is why we say ionic compounds are generally soluble in polar solvents like water, and they are insoluble in obviously non-polar solvents like benzene, ether, carbon tetrachloride, CCl4, and many more. Moving on to the next property, which is brittle nature. Ionic compounds, on applying external force of pressure, are broken into small pieces, and we say they are brittle in nature, and this property is called brittleness. Now this brittle nature of ionic compounds can be understood in a very simple manner. Because we are saying that they are crystalline, that is, they have a regular arrangement of ions in them. So we can refer to a very simple diagrammatic representation of ionic compounds where the oppositely charged ions have a definite geometry, they have a definite pattern of arrangement, maybe something like this, right? So when we apply external force over a crystal of ionic compound, the layers of ions slide over one another and particles of the same charge come near to each other. So if this is an ionic compound structure and we are applying external force over it, the surface layer will get dislocated from its position. The arrangement will not change, the arrangement will remain as such, but the position of ions will change due to the application of external force. So we can see that similar charges are coming in contact with each other, and now instead of forces of repulsion, like this positive is coming in contact, negative is coming in contact, so due to the similar charges there will be a strong repulsion force, and due to which crystals of the compound will break. Coming on to the next property, which is electrical conductivity. Electrical conductivity in any substance is due to the movement of free electrons or due to the movement of free ions. Now when we are referring to ionic compounds, their electrical conductivity is basically due to the presence of free ions. Unlike metals in which the conductivity is due to the movement of electrons, here an ionic compound exhibits electrical conductivity due to the movement of ions either in their fused state or in the soluble state in the polar solvent. Now this is very important to note down because ionic compounds are generally solid in nature. Their common physical state is solid. But in solids, the oppositely charged ions are held together by strong electrostatic forces of attraction. So they are unable to move. And when we are referring to electrical conductivity, it is important that ions are movable. They have movement in them. So that is why we say that yes, ionic compounds are good conductors of electricity, but there's a condition applied that either the compound should be in its fused state. Fused state refers to the molten state of compound, or it should be in the form of its aqueous solution. Right? So NaCl, sodium chloride, if we are taking it in the solid state, it is not a conductor of electricity. But the same compound, when either taken in its molten state or taken in the form of its solution, will become a conductor of electricity, because in these two states, in these two forms of the compound, the ions will be free to move. So these are the different the properties of ionic compounds. Now we come to the occurrence of metals. Occurrence of metals. All metals are present in the Earth's crust either in their free state or in the form of their compounds. The most abundant metal in the Earth's crust is aluminium. Then second most is iron. And the third most abundant metal is calcium. Now here I have used two terms, free state and combined state. So let's take them one by one. First is the native state, which I am calling to be free state, or it can be called as uncombined state, or it can also be said to as elemental state. So a metal can occur in native state or elemental state, and it is said to be in this state when it is found as element or as metal in the Earth's crust. The metals which are very unreactive or which are lying at the bottom of the activity series, they are found in their free state because they have very less tendency to react with other substances like oxygen, water, carbon dioxide, or maybe the other metals or non-metals, and that is why they occur as element or in their uncombined state in the Earth's crust. Common examples of such metals which can occur in their native states are like silver, gold, platinum, copper, etc. So these metals generally occur in their free state in the Earth's crust. The second state of occurrence of metals is their combined state. A metal is said to occur in a combined state if it is found in nature in the form of its compounds. Obviously, the name is telling itself. Combined means it is in the form of its compound. Now, those compounds can be oxides, maybe sulfides, maybe carbonates, halides. It can be of any nature. And metals which are reactive, highly reactive or moderately reactive are found in their combined state. Common examples of such metals are like sodium, magnesium, calcium, potassium, aluminium, and many more. Now it's important to note that some metals, basically there are two metals, copper and silver. These two metals are such that they can occur in both the states, free as well as in their combined state. So these examples are important to be noted down. Silver and copper both can occur in their native as well as in their combined state. Now another term related to the occurrence of metals is minerals. The natural substances in which metals or their compounds occur either in native state or in combined state are called minerals. So simply we can say that minerals are what? They are the natural state of occurrence of a metal. Any metal which is either occurring in its native state or in its combined state, that state of occurrence will be called mineral of that particular metal. Now obviously when I'm saying that minerals are occurring in the Earth's crust, definitely they are not going to be pure. A number of impurities, maybe earthy impurities, dust, dirt, or impurities in the form of compounds of other elements are present associated with that particular mineral. So first of all, mineral is what? It is only the natural state of occurrence of metal. And minerals are not pure, they contain different types of impurities. The impurities which are associated with minerals are collectively called gangue or matrix. So gangue or matrix is a term given for the impurities which are associated with minerals. Now, mineral from which the metal can be conveniently and profitably extracted is called ore. Again, a very important term associated with metals. Minerals can be more than one, they can be a lot number. Like suppose there's a metal called X. This is just an hypothetical example. Suppose there's a metal called X and it is occurring in the form of A, B, C and D in the Earth's crust. Maybe in free state, maybe in combined state. So all these A, B, C, D will be the minerals of metal X. But if I need to extract the metal X from any of its minerals, I will choose that mineral from which extraction of metal will be more convenient, it will be more profitable, economic and easy, right? So maybe I did some analysis and I found that among these four minerals, mineral B is the one from which metal X can be extracted most profitably and conveniently. So this mineral B will be called the ore of that metal X. Others A, C and D will be just called minerals, but B will be the one which will be called the ore of that metal. So there's a clear-cut differentiation, a clear-cut distinction between minerals and ores, and we can make a general statement here which is very important also, that all ores are minerals, but all minerals are not ores. This is very important to note down. All ores are minerals, because we are saying ores are what? They are those minerals from which the metal can be easily extracted. But all minerals are not ores. Like in the previous example, A, C and D are just minerals, they are not ores. We can understand this by a practical example. What I've taken was a hypothetical one. Now I'll take a practical example, and let's take the metal aluminium. A very common example. Aluminium occurs in the Earth's crust in many forms. Like it occurs in the form of bauxite, whose formula is Al2O3.2H2O. It occurs in the form of China clay, whose formula is Al2O3.2SiO2.2H2O. It occurs in the form of cryolite, whose formula is Na3Al(F6). It occurs in the form of diaspore, Al2O3.H2O. So all these are different forms of occurrence of aluminium. So what I can call is, all these are minerals of aluminium. So bauxite, China clay, cryolite, diaspore, all are what? They are minerals of aluminium. But if I need to extract aluminium, I will go for bauxite. So bauxite is the ore of aluminium. Now coming on to the types of ores. The most common ores of metals are oxides, sulfides, carbonates, sulfates, halides, etc. In general, very unreactive metals like gold, silver, platinum, etc. occur in their elemental state, that is in their free state. So these are the minerals of, or the ores of these metals. But metals which are slightly reactive, for example copper, lead, etc., they occur in the form of their sulfides. Like copper occurs as CuS, lead as PbS, and reactive metals like manganese, aluminium, etc. occur as their oxides. Manganese will occur as MnO2, aluminium will occur as Al2O3, and most reactive metals like calcium, potassium, magnesium, etc. will occur in the form of their salts, carbonates, sulfates, halides, etc. So these are the common ores of these metals. We can quote some more examples of ores like iron. For example, metal iron. It has one of its ore as hematite, Fe2O3. Magnetite, Fe3O4. Then metal like sodium, very common ore, NaCl, which is called rock salt. Silver, its ore is AgCl, called horn silver. Calcium, it occurs as CaF2, fluorspar. and many more. Now, why we are studying minerals, ores, occurrence of metals? Because they are important to study metallurgy. All these terms are associated with metallurgy, which is a very important part of metals, study of metals. And what is metallurgy? Metallurgy is the process of extracting metals from their ores and then refining them for use. So, I've already mentioned that metals occur in the Earth's crust in the form of minerals, and some of the minerals are categorized as ores also. So, if we need to use a metal in a particular application, what we need to do is we have to extract that metal from its ore. Now, one very important thing to be noted down here is whenever we are referring to metallurgy, whenever we are studying metallurgy or anything associated with metallurgy, we use the term ore and not mineral, because metallurgy is the process of extraction of metal, and metal will be extracted from its ore and not from its mineral. So one thing very importantly, metallurgy, with respect to metallurgy, the term that is going to be used is ore and not mineral. So if I need to, let's say, use aluminium maybe as aluminium foil, or to make its alloy for making aeroplane parts, so I need to extract aluminium from its ore, which is occurring in the Earth's crust. So this entire process of extracting, mining out the ore from Earth's crust, and then extracting aluminium out of it, and further purifying aluminium till it can be applied to that particular use at that particular application, that entire process is called metallurgy. So we can define metallurgy as the process of extracting metal from its ore and then refining or purifying the metal for use. This entire process, this complete process is called metallurgy. Now, ores are occurring in the Earth's crust. So they are associated with impurities. This I've already mentioned. And the impurities collectively, they are called gangue or matrix. The process of metallurgy depends upon the nature of the ore, nature of the metal, and the type of impurities present. So these three factors are going to decide the method adopted for metallurgy. What are these factors? These factors are the nature of ore, nature of metal, and nature of the impurities present. Therefore, there is not a single method for the extraction of all metals. However, most of the metals can be extracted by a general procedure which involves the following steps. Now, from here onwards, sometimes I'll use the term method, sometimes I'll say it is a step of metallurgy. Now, you need to know the basic difference between step and method. When I'm saying step, it is compulsory to be performed. There is a stepwise procedure involved in metallurgy. First we'll grind or powder the ore, then we'll purify the ore, and so on. So steps are compulsory to be performed. Every step, maybe it can have more than one method. So the type of method which has to be adopted during metallurgy will depend upon these three factors which I've already mentioned: nature of ore, nature of metal, and nature of impurity. So methods are optional, and which method will be adopted will depend upon entirely the nature of ore, metal, and impurity. But steps are compulsory to be performed. So moving on to the steps of metallurgy. First step, crushing and grinding of ore. The second step is concentration of ore. Next step, extraction of metal from the concentrated ore. And the last step is refining of the extracted metal. So these are the four basic steps in metallurgy. First is the crushing and grinding of ore, concentration of ore followed by extraction of metal, and last the refining of the metal. We'll take these steps one by one, starting with the crushing and grinding of ore, the first step. Crushing and grinding of ore is also said pulverization of ore. And as the name, as the step is itself explaining, crushing and grinding of ore, we are basically reducing the particle size of ore. We can understand it like this. And simply the ore which is being extracted, which is being mined out from earth, is in the form of big rocks. Whichever ore is it is in the form of big rocks. So it is first crushed with the help of crushers into small pieces, and these pieces are further grinded in mills, ball mill, stamp mill, and ultimately the ore is converted into powder. So that is why the step is called crushing and grinding of ore. We are doing nothing with the chemical nature of ore. It's only pulverization, that is powdering of ore. So we are starting with big rocks, the big ores which have been mined out from earth. They are crushed, they are grinded, and ultimately at the end of this step, what we get is the powdered ore. Now, what is the reason for this step? Why do we need to perform this step? This is because we are converting ore from rocks to their powdered form. That is, very importantly, we are increasing the surface area of ore. The surface area of ore is increased so that the processes, the reactions which are to be carried out further will be carried out or will be performed more efficiently. So to make the entire process of metallurgy efficient, we need to powder the ore. The second step in metallurgy is concentration of ore. This step is also called enrichment or dressing or beneficiation of ore. These are the different names for concentration: enrichment, dressing, or beneficiation of ore. Now this step involves the removal of unwanted impurities from the ore. So gangue or matrix, which is the term given to the impurities, these are removed in this step. And again, in this step, number of methods are there which can be adopted. Those methods will depend upon the nature of ore and the nature of impurity. In this case, still we have not extracted the metal, and that is why we will consider only two factors here for the selection of method. One will be the nature of ore, the other will be the nature of impurity. And we are going to use a difference in their physical property, maybe difference in their chemical property. Generally it is physical. So we are going to use the difference in their physical properties on whose basis we are going to adopt a method for concentration. So different methods for concentration are: the first method is hydraulic washing. Hydraulic washing, the term hydraulic, it's associated with water. And hydraulic washing simply means washing with water. It is as simple as that. We just need to wash the ore with water. It is also called gravity separation or levitation. Now the principle of this method is that it is based upon the difference in, this is very important, difference in the densities of ore and impurity. So this method is basically adopted for the concentration or the purification of those ores which are heavier than the impurities associated with them. So there is a difference in the density of ore and impurity. Ores of metals like iron, tin, lead are very heavy, while the impurities associated with them are light. So there is a difference in density, and generally these metals, the ores of these metals, are concentrated by this method, hydraulic washing.